All right, hello everybody. Welcome to 2.6 Special Functions. Let's get started. This is a section in the book that honestly is kind of crammed in here in our section, or our chapter of linear functions and relations. That has a place, certainly, but it's definitely different. So kind of buckle up, but you'll see some things that we've seen before. Domain, range, graphing lines, linear functions, that kind of thing. But it's going to be in a different format, so bear with me, but if you've watched this video, I think you'll get a handle on the basic ideas of special types of functions. Alright, so here we go. Let me squeeze this over into the picture. What we're going to try to do today is we're going to write and graph piecewise functions. We're going to write and graph step functions, otherwise known as maybe greatest integer functions. And then thirdly, we want to still be able to determine domain and range of a graph. So make sure that you haven't lost that skill. Alright, so let's get started. A piecewise function. You see that right here? I know it's a weird name. Piecewise function is a function that's written using two or more expressions. You see that here. And we're going to have some conditions if you've already looked ahead. But written using two or more expressions. So the first example, here's how it looks. First of all, the look is the most important. If I have f of x equals, and then the crazy bars, this is, I guess, your, braces or something like that. Anyways, I've got three things going on. I mean, we could have two things going on, two expressions. We have three here. There could honestly be a whole lot more, an infinite amount. So we have three. We're going to deal with each of these individually and abide by the conditions set upon them after you see the if word. So 2x plus 3 only if the x value is less than 1. So we're going to have an abbreviated version of the line 2x plus 3. So if we take the line 2x plus 3, if I go over to my graph, we'll do these individually. Just kind of follow my hand for a second. 2x plus 3 has a y-intercept at 3. So if I go up 1, 2, 3, I kind of crossed it. My line's a little off, but it's crossing there. I want to know about the x values that are less than 1. So I go up to the 1, over to the 1 on the x, go up, and there's my open dot. If it's less than 1, I cannot be equal to 1. My slope over here is a 2 over 1. So if I start at my y-intercept and go up 1, up 2, and over 1, I'm actually on the x value of 1. Again, my condition says I can't be equal to it, so therefore, I'm going to put an open circle, and then I have that dot, I have my my y-intercept dot, and I go down 1, down 2, over 1, I go down 1, down 2, over 1. So I connected my line, as you see there. Has a positive slope going up, but it stops where the x is 1. And it's open circle because I cannot be 1. Alright, next. The equation is negative x plus 2. If my x is greater than or equal to 1 and less than or equal to 2. Notice how I said that. It's basically, guys, between 1 and 2. Think of it that way. It's between 1 and 2. And if you notice the equals bar, it can be equal to. So therefore, we're going to have closed circles. So if I look at it, I've got a y-intercept of 2. But if you notice the y-intercept actually is right here on the graph, it is outside to the left of the parameters of 1 and 2. So what I've got to do is I've got to go down and over using my slope. So if I started at 2, I go down 1, over 1. Well, there's my first dot. So I'm equal to 1. So I put a dot down, and I go down 1, over 1, and I put a dot down there, because that's at the x value of 2. Now, since I can only be between 1 and 2, and I can be equal to them, I connect those two dots, and I'm finished. So it's really weird to see the equation of a line, and it only goes from one point to one point that briefly. But that's a piecewise function. It's taking pieces of lines and connecting them together. So, lastly, a constant function, f of x equals 3 only if the x value is greater than 2. So I go find my 2, I go up to where the y equals the 3, and I put an open circle because I'm greater than that, and I connect my line, and I go off to the right with it. It just goes on forever. Now I want you to notice one thing. If you were to put a vertical line down beneath the open dot, it's going to go down to the closed dot. So at the x equals 1 mark, you are equal to 1 at some point. And if you're equal to it there, you cannot be equal to it there. And that goes with the same thing at x equals 2. It equals 2 here, but it does not equal 2 there. So as you go through your piecewise function, there's going to be some overlapping numbers. You see a 2 and a 2, a 1 and a 1. One of those has to be equal to, and one of those doesn't have to be equal to. In this case. Now, in some cases, you'll have open circles everywhere, or you may have closed circles everywhere. So that affects our domain and range. So see if I can get this raised up here. The domain of this graph, if you notice, my arrow right here is going off to the left forever, to negative infinity, on the left and right. So I go up, and I'm going to the right, I still hit all my x values, and I go off to infinity in the positive direction as well. So my domain, if you can see it right here in the bottom left, is all real numbers. On the right, I have my range. If you notice, the range, the highest point is going to be up here at the 5. But I can't be equal to the 5, but I can go less than 5 all the way down. This arrow goes all the way down. So what I wrote, if you can see it, is that f of x is less than 5. Now remember, f of x is the same thing as y. So the y values must be less than 5. Okay? Let me switch slides here. Now what you're going to start off with... Oh, just stabbed myself with a whiteboard. Ow, that hurt. Okay, so what you're going to start off with here is going to be a practice problem for you guys. So if you'd like to copy down on the top right of the screen, f of x equals 3x if x is less than negative 1, negative x if negative 1 is less than or equal to x is less than 3, and then negative x plus 7 if x is greater than or equal to 3. If you want to try that one and ask about it in class for the answer, I can help you out with that. Okay, so that's piecewise function, that's the example. 2 basic examples. We won't get too more advanced than that. That's going to be pretty the nuts and bolts of the piecewise stuff. Okay? Let me get back in this picture. And the next item on the list was greatest integer functions. So a greatest integer function, we'll look at the definition first. It is a type of a step function. Okay? So a type of step function, and then it shows up in these weird bars. You have these brackets that have, like, they call them a double bracket. So I made a bracket and I put a line connecting it to make it look like it was double. So if that's what you want to do, that works for me. It means the greatest integer, 1, 2, 3, 4, and so on, 0, negative 1, negative 2, negative 3, nothing in between, just those whole numbers and their negatives. So the greatest integer less than or equal to the value in the bars. Okay? For example, if I have 3.25, the greatest integer that's less than that would be 3. Okay? Think about that. Not 4, the greatest integer less. Negative 8.4. Well, what's less than negative 8? Negative 9. So that's the next integer less than. Okay, think about those things. So, for example, here is the basic graph. Squeeze it in here. The basic graph of f of x equals the greatest integer function x. What you have here is, if I want to talk about the negative 1, we'll look at negative 1 real quick. If negative 1 was in here, Well, it's the greatest integer less than or equal to -1, or excuse me, 0. I'm sorry, that's 0. The greatest integer less than or equal to 0 would be -1. So I'm equal to the -1, I'm not equal to the 0, so I'll connect those. If I picked +1, what is the greatest integer that's less than or equal to 1? Well, you go down to 0. So I can't be equal to the 1, but I can be equal to the 0. Pick the -1, for example. -1, the greatest integer that's less than or equal to -1 must be -2. So you're always looking down, okay? Think about it that way. And we want to be equal to the one that's further down, not the one you're talking about. All right? So the domain, all real numbers, because technically, guys, we hit every number, and the line connects everything in between. So it's all real numbers. We're touching all of these. The range, however, if you can see that, is all the integers. Because in between vertically, I'm not hitting, like on the y-axis, I'm not hitting -0.5 or 1/2 or 1.5. If you notice, there's a gap in between each stair step. Okay? So it's all the integers, not just all the real numbers. Okay? There's a difference. Let me give you a real world example. I think it'll make more sense. It actually happens a lot in real life. So, next slide. So I've made up my own auto body shop overnight. You guys didn't know that. Not really. So, ESPN update. Sorry. So the real world example for greatest integer. Let's look at automotive repair shop, Bradford's Body Shop. That's what I have now. I charge $50 for any part the first hour and of labor, and then each additional hour after the first one is 35 extra bucks, not ducks, bucks. So if we draw a graph explaining this, I want to first start with a table. If you think about my shop, if I go on the X column, I have hours. On the right, on the Y, f of X, I have the total cost. So on the hours, if I go from you show up at 0 and you stay until 1 hour, I'm going to charge you $50. If you're past the 1 hour mark, 1 hour and 1 minute, up to 2 hours, I'm going to charge you $35 plus the $50, which is $85. So each additional hour that you show up, just a minute past, I'm going to charge you an extra $35, okay? I may not be fair, but you guys know there's places like this and things like this in real life. So each window of an hour is going to increase by $35, okay? Now, over here on my graph, what I have is at 0, I'm going to actually increase it to $50. So if I go 1 hour, I'm at 50. Okay? If I'm at 0, I'm at 50, but I haven't charged you yet. So I have to go to a full hour to charge you. At the 2 hour mark, I go up to 85. Okay? But anywhere in between the 1 hour mark and the 2 hour mark, I'm basically charging you the 85 regardless. So if you start out in the second hour, which is the third hour, go into the third hour, you've automatically got to pay the 120 bucks. So whatever hour you start, you have to pay the higher value. Okay? That's a step function. That's a greatest integer function. All right? So this is how it works in real life. I think you could actually think about where this could occur. It makes much sense, too much sense. People want to make money, and this is an easy way to do it. Okay? Piecewise functions, step functions, or greatest integer. That's what we talked about today. Domain and range play a big role in this. So if you have any questions, come to class with them. Come before school. Make sure you watch the video. There will be a small quiz. And yes, Bilbo, yes, there will be a quiz. And yeah, I'll probably call on you, Bilbo, to get this question asked. All right, back to the class. Guys, always remember, flip, don't flop. Have a good day. Bye-bye.